Aero Engineering Thermodynamics. Unit 4, Air Standard Cycles. Stirling and Ericsson cycles. They differ from the Carnot cycle in that the two isentropic processes are replaced by two constant volume regeneration processes in the Stirling cycle and by two constant pressure regeneration processes in the Ericsson cycle. Both cycles utilize regeneration, a process during which heat is transferred to a thermal energy storage device called a regenerator during one part of the cycle and is transferred back to the working fluid during another part of the cycle. The regenerator is a device that borrows energy from the working fluid during one part of the cycle and pays it back without interest during another part. Stirling cycle. The TS and PV diagrams of the Stirling cycle, which is made up of four totally reversible processes. 1 to 2T equals constant expansion heat addition from the external source. 2 to 3V equals constant regeneration internal heat transfer from the working fluid to the regenerator. 3 to 4T equals constant compression heat rejection to the external sink. 4 to 1V equals constant regeneration internal heat transfer from the regenerator back to the working fluid. Stirling cycle. The execution of the Stirling cycle. Stirling and Ericsson cycles. The Ericsson cycle is very much like the Stirling cycle, except that the two constant volume processes are replaced by two constant pressure processes. Both the Stirling and Ericsson cycles are totally reversible, as if the Carnot cycle, and thus according to the Carnot principle, all three cycles must have the same thermal efficiency when operating between the same temperature limits. Isentropic efficiency. An ideal process should involve no irreversibilities since the effect of irreversibilities is always to downgrade the performance of engineering devices. Thus, the ideal process that can serve as a suitable model for adiabatic steady flow devices is the isentropic process. The isentropic process involves no reversibilities and serves as the ideal process for adiabatic devices. Isentropic efficiency. A parameter that expresses quantitatively how efficiently an actual device approximates an idealized one. This parameter is the isentropic or adiabatic efficiency, which is a measure of the deviation of actual processes from the corresponding idealized ones. Isentropic efficiency of turbines. The desired output of a turbine is the work produced, and the isentropic efficiency of a turbine is defined as the ratio of the actual work output of the turbine to the work output that would be achieved if the process between the inlet state and the exit pressure were isentropic. Isentropic efficiency of turbines. Usually the changes in kinetic and potential energies associated with a fluid stream flowing through a turbine are small relative to the change in enthalpy and can be neglected. Then the work output of an adiabatic turbine simply becomes the change in enthalpy, where H2A and H2S are the enthalpy values at the exit state for actual and isentropic processes, respectively. Isentropic efficiencies of compressors. The isentropic efficiency of a compressor is defined as the ratio of the work input required to raise the pressure of a gas to a specified value in an isentropic manner to the actual work input, when the changes in kinetic and potential energies of the gas being compressed are negligible. The work input to an adiabatic compressor becomes equal to the change in enthalpy.